I'm missing what? Ah, you're right. My units would have been crazy. So, right, you're saying I was careful over here. I put my mu in. But then over here, what I needed to do when I wrote, where's my force friction? So force friction, I see. So when I substitute in for force friction, I need to multiply by mu sub k. And so I believe this guy needs the mu sub k. Because am I right? No. Too many steps at once. Force friction is right here, the minus sign. So it goes right here, right? You agree? I'm going to squeeze it in right there, my mu sub k. All right, very good. So you notice that mass appears in every term in this. Even though there's friction in the problem, it's still the case that mass drops out, right? So I can redraw this and say, oh yeah, g. Oh, and also look at g's here. Both these guys have a g in front. So I can take g sine theta minus mu k times cos theta equals a sub x. And look, I've already isolated. So a sub x, what does it equal? Well, it equals a difference between two trigonometric functions. So first of all, does this thing have the right units? This is an acceleration. This has units of acceleration. Sine and cosine don't have units. Mu is a coefficient that does not have units, right? Mu relates two forces, two magnitudes of forces. So mu itself doesn't have units. So good. The units look good. So far, so good. Right? What about limiting cases? Or for that matter, what about sine? So let's just write the sine. Is the acceleration, let's see, provided, let's see, let's do limiting cases. First, let's do limiting cases. So limits. So if I let mu k go to 0, that goes back to a problem we've already solved. So we know what the answer has to be. If I let mu k go to 0, that's gone. And I just get g sine theta as the acceleration. And that's what we got last time when we just did it without friction. Remember that? So that's good news. It means that this equation is looking pretty good, right? Notice that the acceleration for a non-zero mu is reduced. It goes down because of that minus sign compared to what I had before. The acceleration is lower when there's friction. Does that make sense? Yeah. If there's friction in the problem, and the block's lying down, and I turn up the coefficient of friction. Maybe I put, there's more and more sandpaper when I go on the slope or something, and so the coefficient of friction is going. Yeah, it's going to experience a lower acceleration. So that makes sense. Good. So this equation makes sense. I think it's correct. Good. All right. So that's how to think about friction in a problem when you've got something sliding down an incline. We had to think about the y direction in order to figure out the normal force. But other than that, once we did that part, we were able to substitute it back in, and it's all a one-dimensional problem as far as the motion. Now suppose I have both friction and multiple objects in a problem. You're going to see this on the exams themselves. I'll put some past exams up before the first midterm, and you get an idea what sort of questions I can ask. And something like this can happen, right? You can have a situation where you've got some incline, there's an object, and maybe there's friction, right? But you can also have some ideal pulley and a rope with some tension, right? Some object hanging, M1, M2. So you can have situations where there's friction and where there's multiple objects and an incline, all these things, but it's okay. You already know how to tackle all these things individually, or you've seen me do it and you'll get used to practicing these things. You just use all these tricks at the same time. And in every case, you're always going to go back to using Newton's second law and making choices about your free body diagrams and all that kind of jazz, right? So let's think this through. Suppose we're asked in this problem, there's a couple of obvious questions one might ask. One is what's the acceleration? The other is what's the tension? So you could be asked, what's the acceleration? How would you solve that? An acceleration of what? Well, these guys are tied together. It's not going to matter, right? But let's say it's acceleration of mass 2. What's the acceleration of mass 2, right? Of course, if you have friction in a problem, you have to read the problem carefully. It can be set up so that the thing's not sliding, it's holding still. Or it could be that it's sliding. Also, as we mentioned before, if the problem, depending on how big these masses are, you can have a situation, well, actually I'll make two statements. One is that suppose you make these masses at different values. There are some values for these masses for which holding still is impossible, right? Suppose this mass is really big. Well, it might be that this guy can't fight it. The friction is not sufficient to overcome the force from the tension in this rope. There's heavy mass over here. So it would drag that block up the hill if you tried to have it sit still. But maybe if the masses are chosen to be a different ratio, then it could be the case that this guy could hold still and be held in place by friction, right? You could also have a situation where this mass is bigger than that one, so you expect him to, so if you just put him there at rest, he would just start sliding down the hill, and this guy would be raising up. But you could start it off with initial conditions where the velocity of this guy is going up the hill. You start it off by having it slide up the hill. In that case, the initial friction force acting on this block would be pointing down the hill. But then once it reaches, after a while, it would slow down and come to a stop maybe, and then turn around, go the other way. Now the direction of the frictional force changes. You can have all kinds of problems, right? Depends on the initial conditions, depends on how it's described, depends on the relative masses, et cetera, et cetera. But there's some things you can count on. You can count on the fact that if this pulley is ideal, that tension equals that tension. I can label them both with the same T and not separately solve for them. And you can count on the fact that as long as this guy is tight, I didn't draw it that way, as long as the string isn't broken and it's an ideal string, you know that his acceleration in the vertical direction is going to be the same as his acceleration along the slope. And just make sure you get your signs right. So let's define our axes for this problem. I'm going to define this to be the x direction and the y direction. Well, I could use the same axes for this guy, but then see what happens? It makes this problem artificially complicated, right? He's only going to move up and down. Whereas this guy's going to be moving along the x direction, this slant, right? This slope. So what I might do is define this guy to have a vertical axis. Maybe I'll give it some other symbol just so I don't get confused. This is not, of course, the z direction that's perpendicular to x and y. This isn't like x, y, and z. It's just some other axis. And I could have called it y if I wanted, but just be really careful that you know what you mean when you write your equations down. I like to use a different symbol just so I keep my head straight. It's all about bookkeeping and keeping straight what I mean. That's half of the battle, right? So I'll go ahead and define 3 separate axes in this problem just because it makes my life easy. I'll do it that way. So now when I solve it, I say, all right, what's my free body diagram? My starting point for all these sort of problems for mass, well, let's do mass 1. Well, it's pretty simple, right? So I have two forces acting on mass 1. You've got gravity, M1G, and he's got tension T pointing up. Okay, we don't know what the relative sizes are yet. We haven't solved the problem. But I'll just go ahead and make sure the directions are correct and just make them around the same length, and we'll worry later. We'll solve later for if it's bigger or small. So that's free body diagram for number 1. Let's go ahead and do Newton's second law for him for object 1, and let's do it in the I called it the z direction, since that's the only interesting direction of motion. What is the net force? It's let's see, upward is positive, so that's positive T minus M1G equals MA, and I'll call it Z of block 1, right? But right away, we know we're going to be relating the accelerations later. I'll write it this way just to make sure I know where the equation came from, but pretty soon I'm going to write down, let's just call the accelerations A and make sure our signs are right. Okay, great. So what about free body diagram for object 2? Now I've got, let's see, how many forces are acting on block 2 now? What's the first one? Gravity. Tension. Normal force. Friction. Yeah, 4 forces. So I gotta make sure they're all in the diagram because I want points. All right, where am I going? I'm going that way. Force normal. I'm going up the hill. Actually, do I know it's up the hill? Let's say that we're told in the problem description that the block is sliding down the hill. We know that. It's a given. So then I'm confident this is correct. Force of friction. What if I don't know it? What do I do? Because you have to solve some problems sometimes we aren't told ahead of time. this is a legitimate way to go. Just to assume it's going up the hill. You don't know yet. You're told the block is sliding, but you're not told which way it's going. It's okay just to do this, but that means that when you substitute into your equations, if you get a negative answer when you're done for the magnitude of the force of friction, it just tells you that, oh, because of the masses in the problem and whatever else is going on, it turns out that the force of friction, how do I say this? If you get a negative answer when you're done for a magnitude of a vector, that often means that you made some wrong choice in the beginning of the problem, you didn't have enough information yet. It'll turn out that there's going to be problems where that's going to be the case, but what you'll do is you'll just make an assumption, and you'll check your assumption at the end of the calculation. If there's a minus sign in there, and you're confident you didn't have an algebraic error, you'll say, okay, clearly what's going on is that I made the wrong assumption, and at the end it turns out it's going the other way. But in this problem we know. We have certainty that the force of friction is up the hill. We're told M2 is sliding down the hill, so I draw it like that. The next thing I need is the force of gravity, M2G. I'm careful to label that too because there's two masses in my problem. And then I've got the last one. Oh yeah, tension. Which way is tension point? Up the hill or down the hill? Up the hill. Same direction as the force of friction. So 4 forces, right? 3 of the forces are lined up with x and y, as is the acceleration. The acceleration is lined up with x. That's why I chose x and y like this instead of choosing it vertical and horizontal. There is a vertical force in the problem, but these other 3 aren't. So if I use vertical and horizontal axes, I'd be breaking all 3 of these guys up into pairs of components. Just a lot more work than I want. So I'm only going to break them up into components, make my life easy, right? Okay, great. If we were to figure out what the normal force is using Newton's second law, only 2 forces enter. There's the normal force and there's the force of gravity. These guys are both along the x-axis. They have no component. So the equation is the same as it was over here, wherever it was, right here, and it's the same as it was 2 lectures ago when we did it without friction, without any tension. So we know what the normal force is right off the bat. Force normal, and also for block 2, that is. What does it equal? It equals mg cosine theta. And I'm careful to check to make sure that I define theta the same way in the 2 problems I've got here. If I define theta up here in this case and down there in that case, of course I better change sine to cosine. But, okay, good. So I know what the normal force is, and now I can go through and calculate Newton's second law in the x direction for object 2, right? What do I get? I get that, where's my 2-way diagram? Here it is. I get minus t, I get minus force of friction. What is that? That's mu sub k. Thanks for reminding me about the mu times normal force. What is normal force? Oh, it's mg cosine theta. It's the proliferation of terms, but it's just the same thing. It's all the same stuff you've seen, right? What else do I need? There's no component from the normal force along the slope, but there is a component from gravity. Is it positive or negative down the hill? Force of gravity? Yeah, it's positive, right? mg, and again, sine theta. And all this equals mass times acceleration down the hill for object 2. Okay, great. So now I've got my equation, one equation. I've got how many unknowns? I don't know the tension, and I don't know the acceleration. And we're trying to find the acceleration. So I'm halfway there, but I need one more equation. Right? Actually, I need 2 more equations, but all right, so what's another equation I need? Newton's second law for the first guy. Did I already write it down? Oh, I already solved that, didn't I? Oh, yeah, okay, so I got 2 equations, but I have 3 unknowns because the acceleration is different. You guessed it, acceleration for this guy equals, is it positive or negative? Is it positive or negative, the relationship between these? Given my conventions. Nobody has an opinion about this. Is it positive or negative? Positive, I agree. If block M1 goes up, positive z direction, then block 2 goes down the hill. That's my positive x direction. So there's a positive relationship between those 2 accelerations. Didn't have to be that way, just that's how I chose my axes at the beginning of the problem. As we saw over here, we had positive and negative relationships depending on how we define our axes. So one choice you can make, like in this problem, I could have chosen to make the axis on this side going upward in the positive direction, and the axis for this guy downward, and the axis here to the left, or in your perspective to the right. And that way, all the accelerations would have the same sign. Doesn't matter, just make sure you stick with your convention. So I'll do this, and now I can plug all this stuff in. We'll be solving for acceleration. So I want to isolate the thing I don't know. It's tension. What is tension? Well, from that top equation, what is it? T equals ma plus mt. Okay, so T equals m1 plus, m1g plus a. Does everybody agree with that? I think it's correct. Let's see if it makes sense. Yeah, it makes sense. If there's 10 meters per second squared acceleration of gravity, if there were no other forces in the problem, that means that if the acceleration is upward, it's positive, then the tension has to be really big. It has to overcome gravity and be accelerating the thing upward. So it makes sense I have to add these together to get the magnitude of the tension. Yeah, that makes sense. These are both positive numbers. Remember my convention. G is a positive number. I'm going to write it right on my page. Right? Great. So if I stick this thing into this equation now, what do I get? I get negative m1 times g plus a. Okay, all right. Not the algebra today. Won't always be that way. All right. And I've heard that before. All right. M-A. Oh, yeah, we just call it A now. Great. So now I've got one equation with one unknown. You were told what theta is. We know what the, and which M is this? I got to be really careful. That's M2, and I didn't label it. That should be labeled, right? M2. I can't just cancel it out, though, because tension right there, we don't know if tension is proportional to M2 or not. It doesn't have M2 in front. So I better keep that thing in the problem. I better label it. Gotta be careful. Because otherwise I could have looked at this and said, oh, yeah, M, oh, just cancel them all out. You know, that's a mistake. Different masses. Great. And so now I can solve for A. This A appears there. Oh, but it appears over here, too. Let's see. Okay, well, that's negative M1, and it's minus M2. Okay, so I put a minus sign in front. M1 plus M2. Wow, algebra. And that equals positive mu k m2g cos theta. Oh, everybody's going to have an M2 in front now. So I'll do this, M2 mu k. And then I add it. I think I have to add it, right? Nope. I have to sine theta, and I also have g's in front of both these guys. So it's m2g times mu. Impossible to read. I think it's correct, but it's hard to read. You guys don't believe me? What's funny? Is it wrong? Can you tell? All right. Yeah, so one way to try to fool the grader, I like to have lots of smudges and stuff. No. We get exams. Students will have like 5 answers, placed in different places, and like, hey, well, I had it right. No. It's got to be clear, right? So yeah, if this were my exam, I would erase it and write it clearly. In fact, anyway. But anyway, yes. So this is supposed to be an m2g times mu. And I use pencil when I take exams. Some students use pen. Because like in New York City schools, you have to use pen. Because they want to make sure people don't change their, it's because of cheating stuff. But it's really hard for me to get stuff right the first time. I like to work it out with a pencil and then erase when I make a mistake. You can cross out, and the grader understands. You can cross out is not graded, but if I were you, I'd use a pencil. I'd bring an eraser like this big, and I just have like a little pencil. Anyway, m2g, yeah, I think that's, so let's see, at least that's the right units. Let's see if this looks right. Does that look right to everybody? Anyway, no, you don't like it. Yeah. What happened to the m1g? So let's see where that went. You mean right here? Oh, you're right, I'm missing a term. So I need to add m1g to both sides. Oh, excuse me, to the right side, I mean. I think you're right. I think I needed that term. I needed m1g over there. This should just be mu times, yeah, this should be just the same thing as this, and that term wound up there. So I think we have accounted for all terms now. I find really fast and furious, partly because I think I'm sure you're all punchy watching this stuff. It's tedious to watch algebra at the board. I don't usually do all algebra through the entire lecture, but I think it's worth seeing how these things are actually slogged through. A lot of students, by the time the first midterm comes around, still don't really have a feeling for what's involved in solving this kind of a problem, for whatever reason. So I just want to make it really clear. Here are the steps you go through, and here's what it looks like when you work it all out. But when the dust settles, you wind up with an expression. I've isolated A. I divide both sides by this m1 plus m2. But you can just see right now, the units are all making sense. I've got acceleration there and acceleration there, times a mass. This is times mass, and this is all just unitless. This is a massive acceleration. We can keep slogging this thing out and isolate for A, and we do it. It's a more complicated expression when we're done than we had before. Why is that? Well, we have more forces in the problem. We have 4 forces acting on this object, right? And if we're asked to solve for tension, once we have the solution for A, we can plug it in there. Anyhow, algebra. So today I've covered, these are the building blocks for a lot of the problems you can expect to see on the first midterm. Friction, inclines, multiple forces, multiple moving parts that are accelerated or tied together. What we're going to do next time is we're going to talk about circular motion. I'm going to spend pretty much the whole, so far in the, just give me one more minute here. Just give me a couple minutes. So what we're going to do next time is circular motion. You've already seen me swing this thing around a few times, but circular motion is a special kind of motion, in the same way that constant acceleration motion is a special kind of motion. And we'll have special formulas just for the kinematics, for things that are going in a circle. And we're going to have to keep straight about whether things are moving at a uniform rate of speed, whether they're going constant, well, what's called uniform circular motion, where the speed's not changing, as opposed to a situation like this, right? Like this, one of my favorite little demos. I love roller coasters. You get a roller coaster. Yeah, I love this thing. And it goes around. Oh no! I'll get it. So it's terrible. It's coming out of my allowance right there. Anyway, this thing's going in a circle. But think about this. I mean, when it goes around here, is it going at a constant speed? When you're on a roller coaster, you're just speeding up on the way down, and you're slowing down on the way back up, right? It'll turn out that we'll have formulas that are useful for this case as well as the uniform circular motion. They're both really important. In the chapter, so you've already read about circular motion because it's come up in the same places. And it's been sort of insinuated in the middle of other chapters, but I find it to be a separate topic. I like to cover it separately. So we can really focus on Newton's laws first. Once you know Newton's laws, and you're comfortable with this kind of stuff, then we can start applying these same approaches to problems like this. We have roller coasters, you got forces, and where the normal force is not just pointing perpendicular to a flat table. In this case, you can have a normal force that's pointing perpendicular to the track that's all different directions, right? So that's okay, but I just like to separate Newton's laws from thinking about these more complicated cases. And I like to separate the discussion of linear motion and in particular constant acceleration motion, really get that as a solid separate topic before we start thinking about circular motion. All right, I'll let you go. I'll see you next time.